Thanks, Omar. So I realize it's not a very happy place to be between this many people and happy hour, so just bear with me for a few more minutes. It's a long day, I know. So my talk today, as Omar mentioned, is going to be a layer or two removed from the core concepts of networking that you guys have been hearing all day today. But it does reinforce the fact that for building applications that need to stream data for moments of entertainment for billions of people, we really need to have reliant, performant WAN networking. So we'll get into that. OK, so by a show of hands, how many of you have used Netflix before? Good, excellent. So how much time do you guys think we have before we lose your attention and you ditch us and go do something else, like checking your Facebook feed or something? Any guesses? 20 seconds. Anybody else? No? It's a little more than that. It's somewhere between 60 to 90 seconds when you're actually going through your list of personalized recommendations. But it really is a short interval of time. And during that time, we're competing not just for your attention on a streaming service, but also for a whole lot of other activities that you do. And so even though the choice of content makes a plays a big part, the really important thing is that a seamless user experience goes a long way in making sure that we have that brand loyalty and you keep coming back and back. So as you choose to interact with the service and you start figuring out what you're going to watch, throughout your experience, when you sign in, you're browsing through the recommendations, and you're sort of trying to figure out what to play, going through your personalized lists, and then actually starting to stream something, caches play a very important role throughout each and every interaction. And it's our job to make sure that we can deliver that service to you. So here is a typical user request. I don't expect you to read any of that. But the point that I'm trying to make is that of all the various microservices that come together and put together the user experience that you see when you go to Netflix through your favorite device, there's a hidden microservice, we like to call EVCache, that plays a very significant part in trying to build that experience that we get back to you. And so I'll be talking about EVCache here. It's something that's been in production for several years. I haven't done any real work. I'm talking about it. All the people who have done the work, some of them are here, and we can chat more about it. But let's go and talk a little bit more about what EVCache really is. So it stands for ephemeral volatile cache, which is a fancy way of saying that strong consistency is not really a requirement. It's a cache. Data can be there. Data may not be there. But essentially, it provides good enough reliability for us to be able to meet the needs of our requirements. So for those of you who know about memcached, which is a key value store, a very popular one, Facebook does a lot of good stuff with it. EVCache really is a distributed version of memcached. It has tunable replication, which is to say that you can run anywhere from 2 to 9 copies, depending upon what your network architecture is and what your application needs are. It's highly resilient, which means that server instances go down anytime. They do usually, and I'll get into that in a little while later. It is topologically aware, which means that when you have deployed your caches throughout your network, the clients as well as the services are aware of where exactly which network region or which zone they are part of, and so we can optimize on trying to make sure that we can have the right trade-offs between latency and availability. Typically, memcached has a maximum data size limit of how much data you can store. We have provided transparent data chunking and reassembly on top of memcached. So essentially, you can put in anything which is arbitrarily long, and then we make sure that those limits don't apply. And finally, there's a bunch of other functionality that we had to put in just to make sure that we could run this as a production operation, things like a fast cache warmer, secondary indexing for troubleshooting, and things of that nature. Okay, so just a little bit of a glimpse on usage within Netflix. We run across more than several tens of thousands of AWS instances. At peak globally, we hit an RPS of more than 30 million operations per second. And the cross-region replication stuff, which is what I'm going to be talking about, replicates messages across the wide area network at about 1.5 million replications. It's used quite a bit. That's the point of that slide. So let me set the network context for EVCache. As many of you probably know, that our control plane on Netflix is almost exclusively running on Amazon's AWS EC2 instances. And so that's geographically set up between various network regions. Within each region, there are zones of isolation called the availability zones. Within each zone, there are several instances. And EVCache runs on literally thousands of instances within each zone. Now, as you can imagine, things go wrong. Instances can die anytime. That happens actually fairly frequently, sometimes multiple times a day. A whole availability zone can go down or can run into various availability issues. The chances of a whole region having availability issues are much less. It's a rarity. It has happened. What is more likely, however, is when we are pushing code or making a config change, things can go bad. And so we have had to deal with cases where, because of a bad configuration or code push, we've had to evacuate an entire network region. And essentially, at some point, we realized that this is something we really need to build some explicit testing for. And so that motivated what is known as the Chaos Kong. If some of you are familiar with the Netflix Chaos Monkey, well, this is sort of like the bigger version of that, when an entire network region has to be evacuated. So these are the availability issues we are dealing with. At the same time, there are cases when, let's say, a Netflix member is streaming something on their iPhone, and they're literally driving through the continental US, and they end up bouncing between regions from US East to US West. That's a possibility that we have to account for. And even if the availability of the systems are fine, there's always the classic network problems of running into throttling or having to deal with just packet loss. So to address these issues, we've had to build a lot of redundancy in terms of how we've deployed these caches throughout the various regions. And so almost every cache has several instances running within a particular availability zone and across multiple regions, and we do cross-region replication. Okay, so here's a typical usage model for EVCache. As you can see, the server is really just stock memcached process. There's a sidecar running that pulls in the Netflix ecosystem. So you don't have to, we don't really have to touch memcached per se. It includes interactions with the service discovery layer, monitoring, data collection, and things of that nature. The client application simply pulls in the EVCache client, and that client abstracts away all the interactions with the server, as well as service discovery, and so on and so forth. This is a typical workflow for reading something. There are multiple zones here. You can read from a particular shard in a particular zone. If there is a miss, most likely because the node is down, then the client, which is topologically aware, knows that it can simply read off of the corresponding shard in the different zone. When it comes to writing, we follow a simple write-all model, and so each cache in each zone appropriately populates the service. The read is configurable, and the retries are configurable, so we can trade off between how much latency we can tolerate versus how much availability we need to desire, and that's the concept of tunability. So I'm going to be talking a couple of more common use cases. The most common one is just as a local-side cache. So this is the case where you have an EVCache client and a service client, and a service is yet another microservice. So you can simply read off the data if it's available in the cache and be done with that. But if there's a miss there, you can essentially fall back to the service layer, which goes back to some sort of a persistence pack. And then at Netflix, we use Cassandra a lot. It provides us really good availability semantics, but it doesn't provide us with the kind of consistent low latency for reads that we need, and that's where EVCache comes into play. Another one thing to mention here is the demand fill. So once you do have a miss, the service is populating not just back to the service client, but also to EVCache. Another example is using the cache as a primary store itself. So there's no database or no persistence layer backing behind this. The use case for this is for our recommendation engines. We do a lot of intensive computations, and much of those have been essentially split out into a pre-compute layer and sort of the online scoring or online serving. And for that, there's a periodic batch writer that essentially populates the cache. And once a request comes in at a different time, we can simply serve up directly from the cache. Now, note here that, again, this is still a cache, which means that there's no persistence here. But what we've found in practice is that our hit rates are so high, well into the 99.9 percentiles, that essentially, for the small percentage of cache misses, we can simply get by serving general non-personalized recommendations. And so this is a case where a cache is sort of the data store. One unique aspect of EVCache is this idea of having a separate metadata stream. So anytime you're trying to do a mutation, let's say you're trying to do a set or a delete on the cache, the client has smarts that essentially writes off a metadata stream to essentially a message bus. And that allows us to do and enable a lot of additional features. So one example is simply this is how we've actually implemented global cross-region replication. I'll get into the details of that in a bit. It allows us to do secondary indexing, which helps us to do troubleshooting when there are problems going on. We can do fast cache warming. So this is how we do red-black deployments. We actually never deal with trying to make changes or figuring out what shard is available or not. We simply bring up a whole new cluster. That's the advantage of running on something like AWS. And then very quickly use the cache warmer to fire it up in a matter of minutes. And boom, we take down the old system. And finally, there's consistency checkers and other things that we can build. So when we were looking for the technology for how to build a metadata stream, we started out with the simple queue service, which is a package service that Amazon provides. It's fairly reliable and fast, although there have been some occasional spikes in latency. But the key reason why we couldn't use it is because it's a simple queue. There is one consumer, essentially. And if you really needed to have multiple use cases, you would very quickly have to forward that message over into multiple queues, which meant it started becoming a cost play. So we investigated some time, and we picked Apache Kafka, a very, very popular open source pub subsystem. And the main advantage for that is because it's a pub subsystem, you can essentially have multiple different consumers of the same bus. And all of the things that I mentioned in the previous slide were available. And so it also gives us a much better control than we had in the packaged service. OK, so as some of you may know, earlier this year, Netflix launched globally. We were in about 60-odd countries. And at CES, we announced that we are now essentially available everywhere except China. And so there's a lot of work that the team did to try to make sure that we have good cross-region replication to be able to support traffic coming from all of these wonderful locations. So I'm going to talk a little bit in more detail about cross-region replication. So why do we need to do that? Should be fairly obvious. The network context in which EVCache must operate in kind of requires that data is available all throughout the world. What to replicate is an interesting question, and it depends upon what kind of use case you're using. So if you're used if there's a primary store, for instance, for the recommendation systems, you're simply essentially just replicating the sets. You have duplicate caches in your different regions, and anytime there's a set, you duplicate those. When you're using this as a look-aside cache, and there is actually a persistent storage layer, we can do some optimizations. And in that case, we don't replicate the set necessarily. We simply just replicate the deletes, and we essentially invalidate the cache. And we let demand fill whenever there's a cache miss populate. And again, the idea there is that we're trying to optimize how much network traffic we're going to send over between regions. Let's say if we're going from US West all the way to EU West, we want to make sure that we're not sending the traffic that can be optimized in other mechanisms. And so that's the choice that we help our application owners make. Where, even though we are in multiple AWS regions, not every application needs to be there, depending upon what kind of application there is. So that's also a tunable parameter that we can set. And so if I were to summarize the requirements, one of the things that I mentioned at the start of the talk was strong consistency is not a requirement. In fact, it makes our lives that much more easier in the WAN world, because we don't have to deal with things like transactional semantics or partial commit rollover and global locking, which really would have made this problem much harder. And so essentially, it's a model that in many cases is eventually consistent. In some cases, it's just not consistent, and we can tolerate the little time of inconsistency simply based on the use cases. What is a strong requirement, obviously, is reliability, especially for cases where we don't have a backing store. We have pre-computes going on, let's say, in only one region, and if we were never to replicate that, if it's not a reliable system, we will just not have personalized recommendations, which drive 80% of the traffic that comes into Netflix. Asynchronous. So the idea here is that you want to be sure that any problems going over the WAN are not causing back pressure or things that would essentially hurt your local cache operations. So being able to design it in such a way that there's isolation is good. And last but not the least, latency is a very important requirement for us. Our target for the 99th percentile for most of our caches is under 1 second for global WAN replication, and we do meet that target for most of our caches. Okay, so I'll talk a little bit about, there's a schematic here that gives you an idea on what exactly is happening when the replication system is running. So we've got two regions here. There's EVCache set up in both of those regions. There's an application, there's servers. The first thing, obviously, what happens is, let's say a client in region A decides to do a mutation, and the client writes to the servers, but at the same time, it logs off the metadata stream into the Kafka message bus. And then there's a replication relay, which is a subscriber of the Kafka system, gets that message. Now, note that what we're actually sending in the Kafka stream is only information about the write, or so it's a set, here's the cache key, but we're not actually sending the data that's stored into the cache, because that would complicate things, and it would really make scaling the Kafka layer much harder to deal with. So the replication relay here knows about the operation, and then it pulls that data from the cache, the local cache in your local region, and at that point, it has all the information it needs to replicate. It makes a secure connection over the WAN, the replication proxy there, as you would guess, then writes back into the local cache, and then data is ready anytime the application in that region needs to read it. So this is a very simple 20,000-foot overview of what happens. There are some optimizations that we've put into these things. I'll talk a little bit about that. One of those is batching. So as you can imagine, whatever you send over the WAN has cost. So we want to be able to make sure that we're trying to fill up the TCP window appropriately so that we can get the most bang for buck for how many messages we can send without sacrificing the latency too much. Batching messages has actually helped us quite a bit. The other optimization has been around maintaining persistent connections. So this allows us to save the overhead for the TCP three-way handshake, as well as the TLS handshakes that happen. We also keep multiple persistent connections open between various replication proxies and relays. With these optimizations, we have been able to scale and make our system fairly robust. This is the messages process chart. We routinely go over 1 million RPS per second for our cross-region replication. It peaks to about 1.5 million, as I mentioned early on. OK, so nothing comes for free, and nothing is as rosy as it looks. So there's obviously been challenges going through this replication effort. Growing pains with Kafka's performance in general. It's gotten much better over time, but when we started out earlier last year, we were running older versions of Kafka and then just trying to understand change of model, how we were first using Amazon SQS, going to Kafka, things have been different. But now, as I said, we can scale well. The other one was an interesting one. So this is a packets per second limit, which is an inherent implicit limit we weren't aware of until we found out. So this was much more a case where, so you have one instance in AWS, and apparently there is some sort of a limit on how many packets per second you can go out of that instance. And the obvious solution here was to simply deploy more instances while keeping the same amount of RAM, so you're not paying more. That worked for us, but this was mostly an issue we found out in the EC2 Classic, for those of you who are aware of that. In the Classic world in EC2, you don't have access to the physical NIC. And so the limits are much lower than the VPC mode, which is the virtual private connection. So doing that, those limits have gone up. But those are the couple of things that we ran into. There are a few more things that are ongoing challenges. Scaling up and down Kafka clusters is more manual than we would like. Most of the services in Netflix auto-scale, and actually the persistent services and the semi-persistent services like EVCache and Cassandra are the ones that sort of do the heavy lifting, and all the other microservices essentially are stateless. So scaling them completely automatically based on as the traffic is growing is an obvious thing to do, but we kind of have to pay the cost because we're handling the state. And so this has been a bit of a challenge, but we're working on a couple of things to improve. Monitoring can be improved. We have fairly coarse-grained metrics right now. We don't get into the depth we would like to get. We have high-level distributions of latencies, tracking the max latency, as well as how many messages are sent and received. But there's definitely room for improvement here. This was an interesting one. So in the schematic you saw earlier, if the destination EVCache instance on which the replication proxy would write to happen to be down for the particular key that you're writing, then that does cause back pressure into the replication system. Now, there's a chance that happens, but the good part is that because we have a decoupled architecture, it doesn't impact the local cache performance. But this is something that we deal with. And basically, it results in longer latency. In general, we've been able to see that it's acceptable, but something that we're looking to improve. As much as there have been challenges, it's been intensely active period for us and immensely satisfying that we can serve moments of entertainment all through now. There's a couple big gray boxes there we'd like to get to at some point, but we can't control everything. So the road ahead, if I look a little bit, as you can see, we've added tons of redundancy, and with that comes cost, especially when you're not owning your own network. And so one of the things that we've started is a project around cost optimization. And so far, the server was fairly straightforward. It was stock memcached, some monitoring components. But where we're headed is trying to make the server a bit smarter. And instead of a classic simple cache, we're going into a level 1, level 2 cache. And there's a high-performance proxy that we're building called REND, it's written in Go, that would essentially orchestrate between memcached that would continue to manage RAM and our own component, which is based on RocksDB-backed SSD storage. And so we hope we're actually testing in production right now on this one, but we hope to write a little bit more about it in an upcoming blog post. And hopefully we'll be able to have a good balance between optimizing the cost and the performance we need. That's pretty much it. The team is here. For those of you who have questions, if you can maybe raise your hands, a couple of them, you can come to me and ask more. EVCache is open source. Check out the GitHub link. And like everybody else, we're always hiring, so you can reach out to me for that too.
Thank you.
All right.
Couple quick questions here.
Yes.
There again.
Thank you. Again, so you've mentioned some issues with Kafka, well known. Forever going discussion about subpub. The previous presenter said they're going to use ZeroMQ. There are different flavors of MQ. There are neurals such as nuts. Why did you choose Kafka?
What are the issues with Kafka?
Why did you choose Kafka over?
Why did we choose Kafka? Yeah, as I said, the most important reason for choosing Kafka was primarily the ability for us to have essentially a simple multi-consumers for going into a pub subsystem. In general, the approach we use is we try to pick the right tool for the job, and we don't spend too much time trying to do too much benchmarking. Kafka met the core requirements that we were looking for, which is to support multiple different users without having to replicate the data in multiple queues like SQS. So we went with that, and Kafka really has gotten to be a very popular and very well-supported open source system out there, and we're learning from what the industry is contributing back, and yeah, that was the reason.
All right. So let's see. Just to close for today. Actually, well, first of all, yes, thank you very much, Faisal.
Sure.